And thank you everybody for coming to the third session of Asiacrypt 2024 and cryptanalysis of public key schemes. I mean, you are to be commended because you were here, like giving up the desert. So here we have last Ron, and who is going to talk to us about real structures in tensor graphs and how it applies to cryptanalysis. Let's welcome Lars.
Yes, thank you for the introduction. Can you all hear me? I think this is, yes, right. Okay, so I'll tell about work I did together with Simona Samajewska, and we worked on the tensor isomorphism problem. And basically, we found a new approach to attack this problem using a new invariant, and we applied this to existing techniques. So let's dive in. First, let's take a look at basically the motivation for doing this. In the recent call for additional schemes of NIST, there were two tensor-based signatures, namely METS and ALTEC. They both relied on the hardness of the tensor isomorphism problem. So this was for us a natural motivation to look at this problem with our algebraic toolkit and to see what we can do. So let's first define what a tensor is so that we're on the same page. We will be looking at three-dimensional tensors. So these are n by k arrays over a finite field FQ. And we will look at them as trilinear forms. In other words, we will apply vectors to them. And then a tensor is completely determined by its value on the basis vectors, if we choose the basis for Fn, Fm, and Fk. So this means that we can also write a tensor like this. So this is a small example of a 4 by 4 by 4 tensor. And these will be the objects that we will be studying. And because we're looking, we want to look at isomorphism, so we need to have some kind of maps between these tensors. And these maps we define by an action of GL times GL times GL, given by a matrix triple ABT. We just apply the linear transformations A, B, and T to the arguments. So remember, this is a trilinear form, so we input vectors, we can transform these, and then we get a new tensor out of this, which we will call D in this example. And now this will be indeed a group action because we're looking only at invertible matrices. So this will be a group action on the space of tensors, and then we call any two tensors that are in the same orbit, or in other words, if there is a group element mapping one to the other, we call them isomorphic or equivalent in some sense. And then the problem that we will be interested in is the tensor isomorphism problem, which is basically given two tensors that are in the same orbit, can we find the group action, can we find the group element that maps one tensor into the other? This will be the problem that we are interested in. And this is also the hardness assumption for the METS signature scheme. So what about the ALTEC signature scheme then? Well, this basically uses the same problem. However, they have a specific structured tensors that they rely on. And these are the alternating tensors. And alternating tensors can be given basically in two equivalent definitions in autocharacteristic, but first that's fine. So either if two of the inputs of this trilinear form are the same, if that means that the result is 0, then we call it, if for any two inputs, then we call it alternating, or equivalently, if we swap any two inputs and the result negates, then we also call it alternating. And these are equivalent. And this limits the space of tensors that we can look at. It not only limits the space of tensors, it also limits the transformations that we can apply. Because if we would apply A, B, and T that are different, then we wouldn't end up with an alternating tensor again, but with an unstructured tensor. So in this problem, A, B, and T will be equal to each other. And to summarize this, I made the following table. So basically, we have the unstructured and alternating case, the induced matrix constraints for the group elements that we're looking for, and the equivalent problem. And this is interesting. So the tensor isomorphism problem is equivalent to the matrix code equivalence problem. And the matrix code equivalence problem is basically tensor isomorphism, but without choosing a basis. Or tensor isomorphism is choosing a basis of the matrix codes, basically. And then the alternating case is equivalent to the alternating trilinear form equivalence problems. And these are indeed used in cryptography. There's two more variants that aren't used, which are the symmetric and the partial symmetric tensors. But they do have names that appeared in the cryptographic literature, which is cubic isomorphism of polynomials and quadratic maps linear equivalence. We won't go into these, but we saw that these attacks would apply to these problems as well with the necessary changes. All right, so what are the current algorithms for solving these kind of problems? There's basically three kind of tools that are mainly used. One is algebraic modeling. So these matrices, this group element that we're looking for, we can model this as a matrix of variables. And then we can get a polynomial system out of this. And if we get a solution, then we found our solution as a group element as well. Then there is collision-based. We will look into that. And there's and we can to a tensor we can assign a graph, and that's also something we will see. And then basically in our work, what we did is we look at subgraph collision, and this we added to the algebraic model. But I will dive into this a little bit more, a lot more actually. So let's look at collision. What do we mean with collision? A collision for us will be an x and an x prime, such that for one of the transformations, in this case, we are looking at a collision for A, that AX maps to x prime. The reason that we call these collisions are for sort of historical reasons, but this basically means is that we get one vector of information about one of the transformations. And this, in the algebraic model, this gives us some extra information already, because if we would fill this in our definition for the group action, then we see that we get, indeed, we get quadratic equations here, because the B are variables and the T are variables. So this will be a tensor worth of quadratic equations that can help fasten the algebraic system solver, basically. With two collisions, we can do even more, because at that point we can, because these are invertible, we can basically map this to the other side. And now we see that we have linear equations. And in fact, we have two MK linear equations and m squared plus k squared variables. Unfortunately, they are not always linear independent, but in general, this is enough information to solve the problem. So this is why collisions are really a good way to attack tensor isomorphism, because they allow you to solve it once you do find them. Then onto the other variant, the other tool that we use, and that's the tensor graph. And this is basically to every tensor we can assign a graph, and it's given by this kind of long definition. But I will explain it in words as well. So basically, what we do is we take each vector space of the input slots. So recall we're looking at it as a trilinear form, and then we put all these points are then the vertices of our graph. And whenever we take a point from the first slot and the second slot, we draw an edge between them if we fill them in. So for example, let's say the x and y, if we fill them in, then we get a vector out of it. If this is a zero vector, then we draw an edge between it. And we do this the same for the first and third slot and for the second and third. And now one thing to note is that these are not the entire vector space, but it's more like the projectivization of this vector space. And the reason is basically is that this equality to zero is invariant up to scaling. So it makes sense to look at the points up to scaling as well. And then this is a tripartite graph because we have those three point sets, and we can only draw an edge between the point sets and not within a point set itself. And it has a lot of vertices. So there's no chance to store this graph in memory for cryptographic applications. So we do have to, if we want to look in this graph, we have to use some other method to do this. And then let's show an example, because that's always a little bit easier to see. So this would be an example for a 3 by 3 by 3 tensor of a finite field with 5 elements. And you can already see there's quite some points for such a small example already. So this really explodes if you go up in N and Q. The good thing about these graphs is that they lead that the tensor isomorphism leads to a graph isomorphism. So we can build a map from the graph of D to the graph of C by mapping it to AV, BV, or TV, depending on in which point set it is. And then using our definition of C and D, we can see that indeed an edge will always map to an edge, and also the other way around. So this is indeed a graph isomorphism, which basically tells us that this is potentially a really strong invariant for the tensor. And now basically our what we found in this graph, and what this paper is all about, is that we found that sometimes there exists a triangle in this graph. And actually, in the graph that I just showed, it does exist. So here I color it red for you. And we can see this is also the only triangle in this graph. So what does a triangle, if we go back to the definition of our graph, what does a triangle actually mean? Well, it just means that we have a triplet of points, U, V, and W, projective again, such that if we apply any two of them, then they get to the 0 vector. So this is basically algebraically what a triangle means. And now let's look at what the probability is that the triangle appears. Because if we want to use it, we better make sure that we know with what probability it exists and how many there might be. So let's look for this tensor at the triangle E1, 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 where E1 is the basis vector. Then basically, if we apply this, we want E1, so the top slice, and then E1, so the first row, basically. We want this to be the 0 vector. So in other words, all the gray cells need to be 0. So intuitively, this means that we have n plus m plus k minus 2 constraints. And recall that we can pick any triplet of vectors. So this is the amount of degrees of freedom. Rigorously, we can show that indeed the tensor C has a unique triangle with probability 1 over q, bounded above and below with plus minus 1 over q squared, or at least big O of. So we're in quite a good situation now. Well, the triangle doesn't exist always, but we have a good bound on the probability, and then it's also unique. So how are we going to use it? Well, basically, we're going for any tensor isomorphism problem with C and D, we are basically going to check, does C indeed have a triangle? If it does, then that must mean that D has a triangle as well, because tensor isomorphism leads to graph isomorphism as well. Then when we found these two triangles, we basically have a 3-point collision. Because this tensor isomorphism leads to a graph isomorphism, we know that a triangle maps to a triangle as well. And the points, if a point maps to a point, these are exactly the collisions that we talked about earlier. And then basically we solve the system afterwards to solve the problem. So then how are we going to go about in finding these triangles? Because as I told you before, the graph is way too large, so we can't store it in memory and just go looking for triangles by walking through the graph or something, or enumerating. So instead, we're going to take the algebraic approach, and we're going to model it as a system of equations. And basically, then this is the system that we get. So for in order to make sure that C, X, Y dash is the 0 vector, we're going to apply every basis vector to it. And then Well, we got quite a bit of quadratic equations, and we use tri-graded Excel to solve this. I won't go into detail what tri-graded Excel is, but basically what we can see is that these equations are all bilinear, and they're bilinear in 3 different variable sets. And this is why we can use this finer grading to speed up the solving of the Excel algorithm. Then when we found these triangles for C and D, we can basically get an easier problem, because now our matrices will be of the following form. They will have 0 columns in each of the different transformations. And basically what we experience is that this is enough to solve the remaining problem, to linearize this problem in degree 2. Or in other words, these were all solvable in a day for all for at least the level 1 and level 3 formats. So once we found this triangle, this the rest of the problem is quite fast, let's say. So now I talked a lot about the tensor, about the METS case, and tensor isomorphism in itself. But let's take a look what's going to be different for ALTEC and the ATFE case, because these graphs are indeed a little bit different. And the problem is basically that if we look back at the definition for alternatingness, we see that if we apply 2 times the same factor, then we always get identity 0. So basically, any triplet VVV would be a triangle. So we cannot hope to have unique triangles anymore. And so instead, what we are going to do is we define a triangle as a 3-dimensional subspace. And then for any 2 vectors of the subspace, these, if we apply them as input, then it should be 0. And what's interesting about this is basically that we get exactly the same probability bound again. So again, 1 over Q. Now I drew another picture. The light gray cells have to be 0 by definition of the alternatingness, but now it's again the dark gray cells that have to be 0 in order for E1, E2, and E3 to be a triangle. And we can do the rest of the computation to come to this bound again. Again, we are going to look for these algebraically, but now we have to do some trick, because when we are looking for 3 different vectors, we want them to be linear independent. So we do some kind of symmetry breaking by filling in the first 3 variables for each of the vectors. And then we again get a 3 bilinear systems, and we use the tri-graded Excel again. And something interesting happened here, because when we did these experiments, so we didn't have a tri-graded Excel algorithm at hand that we could use for experiments. So instead, we just use Magma's Grubner basis. But if we look at the prediction for the degree of the solving degree that we found, and also that we used for the complexity analysis, then we saw that the actual solving degree was way lower than we expected. So this basically indicates that our new attack is even faster than we can give the prediction of. We were not able to completely figure out why this is so much lower. So now in this case, what happens when we find these triangles? We get a 3-point collision. However, we do not get a 3-point collision anymore, because we now get a collision of subspaces. And we cannot really map the points to the points, because that would be enumerating, and that would be cost way too long. But instead, we get this this transformation. We call that A is B is T. So, but now it has 3 0 columns, except for this square matrix on the top. But this solving the system again took 3 hours for all security levels. Once we found the triangle, the rest is easy, is the main takeaway. And then let's take a look at the results finally. So this is for METS, and recall only with probability 1 over Q we can crack these. So basically we can this complexity only holds with 1 over Q. And the best previous was a graph walking algorithm, and we got these results, so they are somewhat close. What's interesting is this is purely combinatoric and exponential in Q. And this is basically independent of Q and purely algebraic. We didn't take into account here the cost for finding a weak key, let's say. So so this is for the weak key, the complexity. And then for Altec, finally, the results were a little bit worse because there we were able to break practically in half an hour the level 1 parameters in 1/q of the cases. Of course, Altec uses Q is 2 to the 32, so there's a lot less weak keys, but the keys that do have this weakness are, can be practically broken. And then for the other levels, it's as well. So thank you for listening, and I'm happy to take any questions.
Thank Lars for the great talk. Do we have any questions?
Hi, Lars. Thank you very much. It was a wonderful talk. I just wanted to quickly ask maybe just 2 quick questions, one next to each other. So the first one is, does this have any implication for bivariate IP, not just the trivariate version? The isomorphism polynomial, but the 2-variable version.
Good question. It feels like that would be. I'm not sure. Maybe I'm not sure about the definition of bivariate IP, but it sounds like this should apply as well. But maybe we can take it offline to see.
Okay, sounds good. Yeah. And the second thing is you define the graph interpretation of this, but at the end it sounds like it was not useful at all because at the end you formulate everything as a set of equations. So I'm curious, what does the graph interpretation actually bring to the table? Like how can actually be useful?
Yes, good question. So in the end, we don't need the graph interpretation, but it does give intuition for why, and also it gave the motivation to look for these structures, because these triangles suddenly appeared in a few of the cases, which we probably wouldn't have seen algebraically in some sense.
So you literally saw triangles, like when trying graphs?
Well, we were looking for loops actually, and then this triangle already was quite quite an approach to like.
Thank you.
Yeah. Thanks.
Did you find any? So at the moment, you're just sort of probabilistically seeing if keys induce triangles in your graph. But I mean, was there any way that you could tell from a key if you were going to get a triangle? So maybe you could build that into a sampler or something, or is it just kind of random as far as you can tell?
Yeah, good question. We have briefly looked at this, but it seems like basically the certificate to see if tensor has triangle is the triangle itself.
Yeah.
So for level 1, I would say if you really want to use the scheme, you could do like this 1500 seconds during pgen, but if you want. But no, in general, we didn't really find a way to, because this would mainly be interesting during pgen to see if you can throw out maybe the key that you generated.
Mm-hmm.
But no, unfortunately, we didn't find it.
Cool. Thank you.
Thank you for your speech.
Okay. I don't see any other raised hands, so let's thank Lars again. Oh, okay.
Yeah. So thank you for your speech. And during your speech, you have mentioned a code equivalence problem and the fact that the tensor isomorphism problem and the code equivalents are somewhat connected. Does your result have some implications on the code equivalence problem?
It does have, so on the matrix code equivalence problem, yes, because they are in some sense equivalent. One chooses a basis and one doesn't. For Hamming code equivalence, it doesn't have any implications because Hamming code can be more seen as like a 2 tensor, and these really work for 3 tensors. Maybe higher tensors, but we didn't get any result working for Hamming code equivalence. Maybe it works, but I wouldn't know at this point.
Thank you.
Okay, let's just get to the next speaker, but let's first thank Lars for the great talk.
Hello? Yeah. Okay.
So let's welcome Yehu.
Okay. Thank you for the introduction. It will be a bit technical, just the beginning, but we'll try to avoid mathematics in general. So we are going to start to formalizing the things. It's just, let's assume we have a group action. It's just a function. You have a set, you have a group, and then you can operate the group elements with the elements in the set. And then if you operate it in the group, then you can also get an element in the set. In particular, you should send the identity to you should fix the element. Here, the hard problem in group action using cryptography is the vectorization problem. It's given a pair. You have x comma y, then you want to find the element g such that y is equal to the gx star x. So many cryptographic construction use this group action framework. Even more, for some more advanced properties, we need extra properties, let's say. For example, for building treasure signatures or building linkable signatures, you need more properties. No? In this setup, you need, let's say that you, instead of having just one pair, x comma y, you have many of them, a polynomial time, number of that. And then the hard problem is either to find g or determine if, well, they come from a random pair of the x squared. Okay. This topic has been analyzed previously just in the context of linear coequivalence, but not as deep as us, and also in maths, and in particular also in LIP, in lattice isomorphism fusion problem. In all of them, they prove that the number of instances polynomial, you can recover the secret key, but we go beyond. Okay, in the main result of the work is just that, okay, we improve the state of the art. We reduce the number of samples that you need instead of, for example, instead of having n squared, that you can have it with linear number of equations. And in particular, for some construction of linear coequivalence, we have that with only two, you can recover the secret key. So let's start just with the definition of the hard problem in codes, linear coequivalence. So you have two matrix generators, G and G prime. We are going to say that they are equivalent if you have two matrices, invertible matrices. In particular, the second matrix Q should be a monomial. If you can think that it's just a product of a diagonal matrix times a permutation matrix. And then the hard problem is to find this S and Q such that G prime is equal to S times G times Q. This is the general problem, not in practice. We will explain why not in practice. There are some optimization data. So the hard problem, as mentioned, is just to find the S and the Q. So that's the main hard problem on the construction. For example, this includes less construction, linkable signals of less, based on less. more or less. And if the matrix Q is a permutation, then the problem is called a permutation equivalence. And if the codes are not linear, but they are subspace of the matrix subspace over FQ, finite field in that case, and then you call it a matrix equivalence. It's presented by Lars. Just different way to see the problem. Yeah, as I mentioned, this is the general problem, but in practice we don't do this. Like we work with the systematic form. With you can think that it's just the row reduce the echelon form of the problem. In this case, you avoid S. Let's say I will say that later that this is not the case, but this thing like that, and then you only have the Q as a secret. Okay, recently maybe well 2-3 years, maybe 4 years ago, there was this proposal. Okay, let's assume that you have even instead of just x comma y, and the y is coming from the secret, you have also the action of the inverse q or the inverse of q. So that means that you have a systematic form of g times q, and also the systematic form of g times the inverse of q. And just a remark, this one can be easily translated to just having 2 instances with the same secret Q. Just swap it, and then you have 2 instances. And now it comes the whole, okay, we have this mathematical and an algebra description, the how it maps to the group action. So essentially, you are going to have like you're going to work over the set of matrices, invertible matrices, and for the group, in particular monomial. The set is just a quotient because concerning the relation of the, okay, you have a matrix, it's rectangular. In that case, you apply the reduced row echelon calculation, and then you get a representative. So then you define the group action instead of, as mentioned before, like the systematic form of G times Q. So again, I highlight that we only have 1 secret matrix, not anymore 2. So, and similar for the permutation coequivalence and matrix coequivalence, you just replace the groups and the sets. Okay, in the sample complexity. So what do you mean? So let's assume that we have let's formalize the previous problem that I mentioned in the beginning. So you have a polynomial samples, T samples of the 4 GI, and then you have GI prime. GI prime comes from the action of Q star the GI. We are going to define this. We define in the paper in general that this is called the TLCE, the T linear coequivalence problem. So you want to find the Q. Similarly for permutation and for the matrix coequivalence, you have the same definition. You just replace the group and the set and the group action for sure. What was done before a war is there was the Alfonso and the Scala that they analyzed setup for linear coequivalence. And in that case, you have a matrix K times M, and they prove that with K times M, this T equal to that T, then you can recover the secret key. But they were assuming that you have the same S on the left side and the same Q on the right side. This is not the case for the systematic form, because when you apply the row reduced echelon form, you can just get that the S exists, but it depends on Q, and it's different per pair. So the previous algorithm doesn't apply to the setup of used, for example, in systematic form. Okay, the main ingredient for the algorithm, for the result that we have is that, okay, we can represent this problem, like this G prime equals to S systematic form of G times Q as a tensor product. So you can just multiply by you have the code normal, the code generated by G times Q, the secret, and times the parity check. The parity check just demand that you multiply. It should give you this equality equals 0, and then some property with the tensor product. The tensor product here is the Kronecker product, so it just, you can think that is multiplication entry by entry. And the VQ is just you just see the matrix, the full matrix Q, like a list of elements. So that's like a vector, row by row. And in particular, in systematic form, we have a really nice description, because then we know that G is on that shape, identity appended with the M, random M. And G prime is similar, identity explained with M prime. Here, the parity check matrix is just the negative of M transpose on the dative. So that's the reason because it comes from the equation. We are just replacing the tensor product, the matrix H, G, and H prime. And all of these equations are linear. That's an important highlight. So if we have many pairs, then we can just stack all the system that we get, and then we big matrix, big system, and then we can solve with Gaussian elimination if we have enough equation, let's say. In particular, we prove that you can just have t equals or greater than equal than n squared divided by k, n minus k. For more details, I suggest to read the paper. Then you apply Gaussian elimination, you can recover the secret in polynomial time. For the case of k equals to n half, so you only need to try 5 times. But the next slide will show you that we can do it better. The result also applied to matrix coequivalence. In that case, we are not exploiting any structure of the matrices. The only thing that is, we have more variables. We have n, and r, and k. So in any case, it's still polynomial. In particular, for example, for matrix parameters, you have that the m and r and k are equal. So then you can have a linear complexity. And previously it was like cubic. If we recall, it was like k times m. But in the case of matrix coequivalence, the n is the square of k. So we reduce from cubic to linear. Okay, now how we handle to solve with 2 instances. The first observation is that, okay, we cannot do anything just naively with Gaussian elimination because we have less equations than variables. So it will be on the determined linear system. But we came proposing an algorithm for solving this and also for 2LC, for 2LC and ILCs. And the algorithm takes inspiration from Said's work. It's a PhD thesis that I analyzed pretty well the algorithms for attacking linear coequivalence and permutation coequivalence. But it was more focused only on permutations. So the idea of the algorithm is, okay, we are going to just guess one entry of the matrix, of the secret matrix. Recall that the matrix Q is just a monomial, so it's very special. It's a permutation times a diagonal. So per row, we have only one entry different from 0, and also for column, we have only one entry different from 0. We can think that that entry is 1 if we normalize per entry. And then from there, we reduce the system, we reduce the number of variables, and then we try to apply the Gaussian elimination. So it's not directly Gaussian elimination, but we need to do extra steps. And that's what I mentioned. That you have one row, one column, there's only one entry different from 0. The important key here is that if we do this guess, we are reducing the number of variables from n squared to n minus 1 squared. But we are keeping the same number of equations. In this case, we have, because we have 2 instances, we have 2 n squared divided by 2 equations, but we reduce from n squared to n minus 1 square variables. We are going to label here just the A comma A sub ij, the matrix that you apply when you do this guess, the columns that you're eliminating. And B, well, B is the missing part that we are not eliminating, that the one that's coming from the guessing. So the data is simple. As mentioned, is you have the original system, A times, let's say, VQ equals 0. Then we make the guess in the entry ij. We get the reduced system, and then we apply Ricci-Capelli test. So which essentially says that, okay, we have on the left side, we have the rank of the matrices n squared divided by 2 minus 1. And from the right side, it could be that value, or it can be n squared divided by 2. So if it's equal to the left side, then it's a correct guess. If not, so we discard it. We cannot say anything about the guess. Well, we say that is not correct, but in any case. And then the approach is, okay, when you have this reduced system, you are guessing, and then in the end, you end up with a small number of variables, then you can apply the Gaussian elimination on the missing variables. So the probability of having a wrong guess is 1 over Q. So for, I didn't put the details, but for, I suggest you to go to the paper. It's a bit technical. There are essentially n correct guesses. Those are coming from the secret matrix Q, so for this, because of the structure of Q. So for sure we have the n correct guesses, but we can get at most an average n squared minus n wrong guesses. So putting the numbers, so we have this, that the number of expected survival variables after we eliminate the variables with the guessings is n times n squared minus n divided by q. Then we can get an easy, let's say, a straightforward restriction on q. And in particular for this, that means the q equating should be greater than equal than 5 and n equals 2, then the algorithm works with the probability of n 1 over q. The complexity of Ricci-Capelli test is just asking calculating the rank, so it's polynomial. So we know just the omega is the complexity constant for the Gaussian animation calculation, the rank and everything. And we need to do n squared guesses. So we have one guess. For example, we start with this matrix you can show now. Sorry to go this one. We start with the first one, we do a guess, and then if we fail, then we go to the other, and then we go to the other, and so on, so on. So we have n squared guesses that we are doing. But in any case, it's a polynomial number of tries. And therefore, the complexity will becomes most of the part is dominated by the Ricci-Capelli test, but it's polynomial. Mentioned briefly, recall that the inverse linear coequivalence can be reduced to a 2 instance in some sense. And also we show that with a small example, we illustrate that. We show also that the probability is matching in this case, the probability of correctly getting the result, well, it matched with experiments. And we go further with bigger experiments, larger experiments for the 2LCE. So the largest one that we tried was n equals 128, and k is just a half of that, so 64. Just to give an idea, and for less parameters, they are just using the double of the sizes sometimes. Before going to discussion, it's worth to mention that this algorithm that we propose also works for self-dual codes. We additionally provide some experiments with self-dual codes. We didn't put it here, but in the paper you can check for the experiments on that. So now, what are the implications concerning this and the cryptographic constructions? So probably was, as mentioned, there were this problem ICE, which was just proposed, but the authors in that time just suggest, okay, if the ICE is secure, then you can construct a linkable signature. So, but it was left open. That problem was hard. So we show that it's not the case, that it's weak, it's solvable in polynomial time. And additionally, we break one of the constructions of the parameters sets for gas, the threshold signature based on linear coequivalence. And in that case, they assume the setup. They assume that how hard is to determine if two random pairs are coming from the linear coequivalence instance. And just a summary in the end, well, for linear coequivalence, well, at least for results show that you cannot have, based on this construction, maybe further we are going to have it. Linkable signatures, linkable ring signature, you cannot have it. Also the threshold, so you cannot have the pseudo-random functions and updatable encryption neither. The reason is more because even because of the previous state of there, we show that with a polynomial 10 of queries of samples, you can recover the secret. For METs, for multiple equivalence, so we cannot say anything else. We cannot say that the linkable signature is pure or not. The reason is because, well, we couldn't find a way to explode the structure of the secret matrices. For monomial, it's very, very nice, the matrices. That's all.
Thanks to Hu for the great talk. Who do we have from the audience? Any questions?
Thank you, Jesus, for the nice talk. So you're suggesting that linkable signatures don't work because ECDSA is not secure, but potentially some other problem could be used instead to create the next part of the function. Or
Yes, I think if you reuse twice the secret, it's not secure. If someone came with a fancy that okay, you are like masking the secret and using twice, and then you can combine it, then you can have the linkability. But don't try to use it twice.
okay, thanks.
Any other questions? I guess not. Let's just thank the speaker.
Hello? Can you hear me? Hello, can you hear me? Hello, can you hear me?
The third speaker should be.
Hello? Hello?
The Zoom should be on, but we don't see the Zoom screen yet. Don't start yet. The Zoom is not on the screen.
Hello, can you hear me?
Yes, we hear you.
Okay. So,
Yeah, don't start yet.
so let's start.
No, don't. The Zoom is not on the screen yet.
Can you see my screen? I'm sharing my screen.
No, we have a technical problem that's currently being fixed.
Oh, it's not my problem.
So we have Yiming Gao from USTC, who will be talking about attacking ECDSA using lattice sieving. So let's welcome Yiming.
Hello, everyone. I'm Yiming Gao, and my paper title is Attacking ECDSA with Nonce Leakage by Lattice Sieving, Bridging the Gap with Sponier Analysis-Based Attack. This is a joint work with Jinghui Wang, Honggang Hu, and Bingang He. Here is the outline of our slide. First, let me introduce the hidden number problem, HNP. The hidden number problem was proposed by Bo-Yin and Vectorson to investigate the bit security of DB-Hillman. And now it used to analyze the security of ECDSA with partition nonce leakage. There are two main algorithms to solving HNP. First is the lattice-based attacks. They gain better efficiency and require fewer samples. However, it's considered to perform poorly with hard instance and noisy data. In the contrast, the Fourier analysis-based attacks are able to handle more difficult instances, including erroneous input, but it demands significantly larger sample size and computational time. So it naturally leads to key questions. Can lattice-based attack be enhanced by analyzing more samples? And is there a smooth trade-off between the two approaches? In this paper, we give a solution. By analyzing more samples to improve lattice attack, we significantly bridge the gap between the two approaches. In practice, we address the case of 1-bit leakage and less than 1-bit leakage on a 116-bit curve, which is considered extremely difficult in other lattice attacks. Our main contributions are listed as follows. First, we design improved algorithm for solving HMP. We use more samples to construct new lattice with a new parameter x, offering a dimension reduction of approximately log x over L. Second, we prove the existence of a constant which serves as a lower bound of our success probability. Third, we propose an improved linear predicate with high efficiency and prove its correctness. Then, we design an interval reduction algorithm to avoid exhaustive search. Finally, we present a pre-screening technique to pre-select candidates. We also modified algorithm of handling errors. We define HMP with erroneous input to handle practical scenarios in side channel attack and demonstrate the effectiveness of our lattice construction, which offers a greater reduction in lattice dimension. Further, we extend our new algorithm and techniques for solving HMP to address the case of erroneous input. As a result, we set new records of lattice-based attack against ECDSA. We successfully recovered the key of ECDSA instance with 1-bit and less than 1-bit leakage on a 160-bit curve. Here is the table of current lattice-based attacks. We set new record against 4 bits, 1 bit, and less than 1-bit leakage. The one is on Asiacrypt 2021, and 2, 3 were published in CHESS. Now I'm talking about some preliminaries. The first is the lattice. Lattice is defined as integer combination of linearly independent vectors. In this work, we only consider the full-rank lattice, and the volume of the lattice is the determinant of a basis matrix. We use Gaussian heuristic to estimate the expected minimum vector length of a lattice. We use lattice sieving in our main algorithm. The sieving algorithm is the fastest SVP solving algorithm in large dimension lattice. Also, a sieving algorithm outputs a database rather than a single vector. Assumption 1 stated that when a 2-sieve algorithm terminates, it outputs a database L containing all vectors with norm bounded by the square root of 4/3 time Gaussian heuristic of the lattice. Next is the definition of HMP. Given an n-bit size public model Q, and there is a secret integer alpha referred to the hidden number, we are provided with Ti and AI such that Ti times alpha minus AI mod Q is bounded. The problem is to recover the hidden number alpha when m samples are given. In side channel attack against ECDSA, the adversary may know L least or most significant bits of a nonce K, and ECDSA with nonce leakage can be regarded as an HMP instance. At Asiacrypt 2021, Albrecht and Hinger extended the ability of lattice-based attack with their sieving with predicate algorithm. There are 3 main steps. First, construct a lattice which may contain a short vector with the hidden number problem. Then run lattice sieving and obtain a database full of short vectors. Finally, run predicate algorithm to check if the current is correct on these vectors. They also consider the expected square norm of a target vector, and the minimum lattice dimension can be estimated as the minimum integer satisfying the formula under assumption 1. They use recentricity technique and elimination method to construct their lattice as follows. Here is the target vector, and the 0k0 prime is the new hidden number. We improve their sieving with predicate algorithm with more samples. The main idea is that in a large list of HMP samples, some samples have small Ti prime. We then construct a new lattice using these samples. The lattice has larger determinant, but the target vector norm remains roughly unchanged. This enables dimension reduction while satisfying the attack condition. Since the state-of-art sieving algorithm have expansion complexity 2 to the 0.929 times d, so reducing lattice dimension significantly improves the algorithm efficiency and enable to solve harder instances. Motivated by Sun, we decomposed the hidden number k0 prime as alpha 0 times x plus alpha 1. The new lattice is constructed as follows. The Ti prime are required to be small and lead to 2 to the L plus 3 times x times the original sample size. Our new lattice has advantages which lead to sieving 1. It's stated that the reduction of lattice dimension between our lattice and Albright and Hinger's lattice is given by approximately log x over L. We also theoretically analyze the success probability. Under the assumption 1, theorem 2 says that there exists a constant lower bound as the success probability of our algorithm. We conject this constant is 0.5, but we are unable to prove it. Next, I will talk about the predicate algorithms. The predicate algorithm is to check if the candidate vector is correct. At Asiacrypt 2021, Albright and Hinger used nonlinear constraints. Specifically, their predicate check if the hidden number is the secret key in ECDSA, which involves time-consuming scalar multiplication on elliptic curves. In Chess 2023, Xu proposed a linear predicate algorithm and claimed higher efficiency than the non-linear one. In this work, we improved the linear predicate. Our predicate operates on a two-dimensional vector and determines if the candidate vector satisfying the linear constraints of a set of samples. If all conditions met, reveal the hidden number, else return false. Compared to Xu's predicate, we use only last two elements of a candidate vector to avoid unnecessary vector inner product. Second, the HMP samples used in step 2 are distinct from lattice construction samples because in the sieving database, the vectors are inherently shorter. Finally, we correct Xu's linear constraints, which is actually an identical equation. For our new lattice, recall that the transformed hidden number K0 prime is decomposed as alpha 0 and alpha 1. But the target vector in our lattice only contains information about alpha 0. So we need new predicate. The input of new predicate algorithm is the candidate of alpha 0, and it should output K0 prime or false. A naive approach is to exhaustive search over all possible values of alpha 1, which lead to time complexity of OX. When X is large, it becomes impractical. To address this issue, we propose an interval reduction algorithm to reduce the complexity of big O x to the big O log square x and design the predicate of new lattice. The input of interval reduction algorithm is an interval that may contain the hidden number, and it outputs a set of intervals. Then we do exhaustive search on those remaining intervals. The expected time complexity of the algorithm is big O of log square x. Moreover, we present a pre-screening technique to eliminate majority of incorrect candidates before running the interval reduction algorithm. It involves only a few linear operations and doesn't increase the sample cost. We conduct experiments on HMP 256 with 2-bit leakage, and x is equal to 2 to the 50. The interval reduction algorithm offers 2,000-fold speed up compared to the exhaustive search, and combined with pre-screening technique leads to almost 4,000-fold speed up. In the next section, I'm going to talk about the hidden number problem with erroneous input. In such practical side-channel attacks, errors often appear in the data. For ECDSA loss-leakage attack, errors lead to erroneous HMP samples. In previous lattice attack, they perform poorly with this situation, and many work just assume error-free input. The existing solution lack detailed analysis and have limitations. However, Fourier analysis-based attack demonstrates stronger rootedness to errors, highlighting a gap between the two approaches. We give a solution of handling errors. We define HMP with erroneous input based on ECDSA non-leakage models and demonstrate effectiveness of our new lattice construction. Then we extended our algorithm to enhance the lattice ability to handling errors. As a result, we significantly narrowed the gap between the lattice-based attack and Fourier analysis-based attack. The definition of HMP with erroneous input is derived from ECDSA non-leakage with errors. We assume that with probability 1 minus p, we obtain the correct value of L bits of case least significant bits. And with an error rate p, we only obtain a random integer instead. For lattice construction, x is the same, but the expected square norm of target vector and the embedding factor tau changes with error rate p. This construction also leads to dimension reduction. Surprisingly, the reduction is larger than error-free situation and becomes larger when p gets larger. The parameter x can be viewed as a balance to the error rate p. For a higher error rate, we could use more samples to increase x to keep the lattice dimension and the time complexity unchanged. We also modified algorithms such as linear predicate for erroneous input. In this situation, the previous predicate can't be used directly. Recall previous predicate, it tests on each HMP samples. Once a sample fact false, it returns false. However, a single failed test doesn't necessarily imply an incorrect candidate. So we collect samples and count the number of past samples m. If m exceeds the threshold value, we think it's correct. Otherwise, we reject it. We also prove the correctness of this predicate. As stated as theorem 4, the algorithm has an overwhelming success probability. We use Chernoff bound to prove it. Then we enhance the pre-screening technique for erroneous input. Different with predicate, the goal of pre-screening is to retain the correct hidden numbers, rather than eliminating all incorrect candidates. The strategy is similar that we discussed the hidden number candidate if more than threshold value samples are non-compliant. For the previous interval reduction algorithm, it requires error-free samples, or it may include the correct candidate with erroneous samples. To maintain the usage of interval reduction algorithm, we designed the subsampling technique. The idea is to random choose samples from a pool and hope that we could choose error-free one for many times. We could set success probability close to 1 by choosing parameter. Finally, I will talk about the experiment of our attack. Our source code is available on GitHub. The lattice sieving algorithm is based on the lattice sieving in Jessica, and we use BKZ20 to pre-processing the lattice spaces. We categorize instance into 3 classes based on estimated dimension. They are easy, medium, and hard one. And X can be adjusted to keep balance between time consumption and the number of available samples. Here is a table of easy instance. Our algorithm performs better even we don't have additional samples. And with additional samples, the cost time decreases. And for medium instance, the speed of our algorithm became more significant. For hard instance, we set new records. We break ECDSA 512 for 4-bit leakage. And for 1-bit leakage, breaking ECDSA 161 is considered quite challenging in previous lattice attack. And for less than 1-bit leakage, only Fourier-based attack could handle this situation. And our work is the first lattice attack result. Here is the table of our new records. Thank you for listening.
We have time to relay some questions. Any questions from the audience? Yeah.
Can you explain why the randomness model is how you defined it? Why is this the realistic model?
We derive the definition HMP with erroneous inputs from ECDSA loss leakage with errors. We assume a model with this probability.
Okay, I see, but there is no like real life expectation that this is how leakage looks like.
Yes, it's the leakage model that we assume.
Okay, I see, thank you.
Any other questions? So, Yiming, could you tell us if you tried this on any like real equipment and gotten any actual experimental results, or like did you actually do side channel analysis with oscilloscope and that stuff, or is this just
We do not do real side channel attacks. However, we apply our algorithm on the database of real side channel attack, like TPM4, a database. The source code is available on the GitHub.
Thank you. Any other questions? If not, let's thank Yiming. Concludes the session, and